now we have done building our datasets, and we can start build our models. So the first one we'll build is our encoder. We'll take embedding dimension. So this is the length of the embedding vector that we are gonna use. And the hidden dimension, which is the length of the hidden states in the encoder. Stack, which is how many stacks of RNNs you want to use. Dropout, let's put a default of 0 here. Input dim, and let's say the default is numbers 1. It's better to do numbers 2 actually, because the encoder will take French, which is our second language. So let's store some variables into our class. And now we are gonna use rnn.embedding to build our embedding layer. And we'll intake our input dim, and the output will have a size of the embedding. And our RNN layer, we will do a GRU here. Embedding, hidden dim, .gru. Stack, and let's do bidirectional is true, and also our dropout. And just a personal habit, I always use batch first is true. And since we are using a bidirectional model for the encoder, it's impossible to use bidirectional for the decoder, because we are decoding word by word. So when we are gonna copy our final encoder hidden state as the initial hidden state of the decoder, the size will give us troubles. So we need another layer to shrink this concatenated hidden states of the bidirectional encoder into only a single hidden state. So we're gonna use a fully connected layer. Let's say dot linear is originally hidden dim times 2, and the output will be hidden dim. So this essentially turns the concatenated 2 hidden layers into only 1. And our forward function. So this input will actually be a tensor that has a shape of batch size by the constant length of our source, which is 10 here. To save some computing time, we're actually not gonna pass the padding zeros into our encoder models during training. So how do we skip the zeros? We are actually gonna use something called a pack padded sequence, which basically packs the padded batches before sending that into the RNN. And the output of the RNN will also be the packed version. So we will then need to unpack this back into the desired dimensions. So I will gonna show you how to do this. First, we're gonna need to know the lengths of each entity in our batch. And we can use the torch.count_non-zeros function to do this of our input at the first dimension. And simultaneously, I will show you an example here. Let's say we have a arbitrary tensor. Let's say 1, 2, 3, 4, 5, 6, 0, 0, 7, and the remaining are zeros. And I want to reshape this into 3 by 4. Alright. And we print this tensor. Yeah. So we have 4 non-zero elements in the first row, 2 in the second row, and only 1 in the last row. So let's try source length. Let's see if that's correct. Yeah, so we get 4 to 1 as expected. Oh yeah, and we will need to embed our inputs by using our specified layers. So just to make things clear, this thing has a shape of batch size. Let's call it n, okay? And this embedding has a shape of batch size by embed size or embedding. Then we are gonna need the tool to pack the padded batch, which is n.utils.rnn.pack padded sequence, and the first argument is our embedding, and we want to tell it the length of each entity, which is source length, and they are expecting this argument to be on the CPU, so we will move it from anywhere to CPU. And as a habit, batch first equals true. So let's see what this does. Yeah, so this is the packed sequence. What this means is that our first batch has a length of 3 because the first column has 3 non-zero elements, being 1, 5, and 7, corresponding to 1, 5, and 7. And our second batch has a length of 2, being the 2 and 6 here. And our last element of the second batch is 0, so it's skipped. So we have 2 and 6. And our next batch has a length of only 1, being the only non-zero element 3 here. So 3. And same for our last batch, only a 4 here. And length 1. That's how it works. And after we have packed the batch, we will need to try to unpack that back to our normal shape. So how to do this? Let's say unpack equals packed sequence, and the input is our packed version. Yeah. So this returns to the original shape. But I do want to point out that this one accepts another argument called total length. If I put 4 here, this is the length of the batch. It will be the same, but I can put anything here. I can put 5, and it will add another row, another column of zeros. So this is very important for us. Why? Because in case our batch has a column of fully zeros, then our reshaped packed sequence will missing that column of zeros, which will mess up our dimensions, and we don't want that. So always in our model we will specify this total length. I can try to show you this. If I put 0 here and I don't have this total length, it's missing a column of zeros. So yeah, that's really important. So let's go back to our encoder. Our output of the RNN and the hidden state will be self.rnn of the embedding. And this output here is actually the packed version, so I will say output packed. So what's the shape of our hidden state? I will need to explain this more clearly here. As you can see, we have both the stack and bidirectional arguments here. So what Pytorch will do is that it will first concatenate all the final hidden states for all the stacks in each direction, and then it will concatenate the stacked final hidden states for both directions. So the final shape of the hidden tensor will be like 2 directions times the stack and the batch size and the hidden link. Now let's unpack our output first. Output is and our total length. This is crucial. This is the first dimension of our input. And what we will further do with our hidden state, our final hidden state, is that we will reshape this into the correct dimensions for our decoder to use later. So we need to firstly split that into 2 parts. Let's say hidden 1 equals the first half, and our hidden 2 equals the second half. So this one is on one direction and this one is on another direction. And we concatenate them in another direction at the last dimension for us to use our linear layer. So this one will have a shape of stack by batch size by we essentially move this 2 to the last dimension, so it's 2 by hidden thing. And yeah, our output, I forgot to mention this. This output is actually the concatenation of all the hidden states in our encoder on the final stack. And we do have both directions here. So the shape will be batch size by the length of our source sentence. Let's call it L subscript source. And they decided to put the 2 at the final dimension. So 2 by hidden D. And now we can shrink our hidden state to the proper size. So yeah, don't forget our activation function. Let's try redo here. And eventually we will have a shape of stack by batch size by hidden link. And that's pretty much it. We can now return our output tensor and the hidden tensor for the future use of our decoder. So what else? Yeah, I might be converting this GRU into an LSTM in the future, and we will be having an additional cell tensor. So I will reserve one space here using none. Now we're ready to code for our decoder. So in our constructor, we will pass in the embed dimension, hidden dimension, which should be the same as the hidden dim of our encoder, and the stack, which also should be the same as the stack of our encoder. And input dimension to the RNN layer, I will call it input dim, say 512 as default. Output dim with a default of the vocabulary size of English, which is numwords 1. Let's call this RNN input dim just to reduce some confusion. And dropout with default 0, and our max length being the same as in the encoder is the length of the source. So max length 2, which is for French. And let's store some variables to our class. Now we can build our first embedding layer with the maximum value being the output dim, and the size will be embed dim. Dropout. So let's leave the constructor as it is now for a while, but I will come back later. So let's look at the forward function first for now. And we're passing in the decoder input, which will be a single column being a batch. The previous hidden state, the encoder output. So in order to reserve a place for an LSTM modification, I'm gonna leave a cell here, but it's not to be used in this GRU version. Yeah, so let's leave it as it is now, and we will add some more stuff if needed. So first we open the batch size, big N, which is the shape of the decoder input at the 0th dimension. 0. And we want to ensure that this batch size of the decoder input is actually the same as the batch size of our previous hidden state. And the batch size of the hidden state is at the dimension 1. Also, we have our length of source equals to the output of the encoder's shape at the first dimension. So it's here. This is the output of the encoder, and this is the length of source here. And we also want to ensure that this length of source is equal to our max length. So self.max length. We can go to make our embedding of the embedding of the decoder input. And this will have a shape of batch size by 1 by embedding. This one is because we are feeding the decoder inputs column by column. And here, as you did notice that the encoder output has a 2 times hidden dimension at the last dimension. This 2 comes from the bidirectional. We don't want the 2 here. Instead, we want it to be in the middle dimension. So I'm gonna do a manual reshape because the default reshape function might mess up the orders of things. So let's say encoder out reshaped. The concatenation of the encoder output, I mean the first half of the encoder output at the last dimension. So it's 0 to hidden dim, and this same encoder output, and we take the second half from this hidden dim to the bottom, and we concatenate them as dimension of 1, and afterwards this will have a shape of batch size by 2 times source length by hidden dim. So we are gonna compute the attention slightly differently from what I have introduced you in the diagrams at the beginning. So instead of directly matrix multiplying the encoder outputs and the final hidden state, we are gonna take them and go through fully connected layers separately, just to enable it to find some useful features which may enhance our performance. So let's flatten this first. We will do encoder out reshaped dot reshape again with batch size 2, because we have 2 directions from the encoder, and the final dimension will be source length by hidden dim. I don't like using -1 here because it will conceal any bugs if there are. And for our hidden state, we also slightly reshape that. Let's call it flat, because we are orientating the hidden state at the final stack from the last run. and we add another dimension in the middle and reshape it to batch size by 1 by hidden dim. Actually, we do not need this reshape here because it's automatically this shape, but it's fine. So why do we only take the hidden state from the last stack? That's because we need to match the shapes of the hidden state with the encoder output in order to do matrix multiplications later. We cannot use all the hidden states from all the stacks. So as I said, we are gonna need linear layers for the encoder output flat and the hidden flat. So I'm gonna add another argument here in, let's call it W size, with a default of 256. Or taking an input with the last dimension of hidden dim by max length, right? Because here is the hidden dim by max length. This max length and the length of source are equal, and the output will be, we'll swap this hidden dim with the W size. So W size by max length, and the fully connected layer for the hidden state is taking an input with the final size being the hidden dim, and the output final size will be the W size. And let's do self dot W equals W size for using the forward function. Yeah, so we can use them now. So just to make our lives easier, let's call this P equals activation of the fully connected for encoder output applied to the encoder out flat. And I think now we can reshape this back to a more useful shape. It should be batch size by 2 times length of source and self dot W. Right? The first 2 dimensions are identical to it at the beginning, and the last one, since we have the linear layer, is now W instead of hidden dim. And for the hidden state, after the linear layer and resizing, let's call it Q. It will be FC hidden for H flat, then reshaped to let's put the redundant dimension at the zeros place, 1 by batch size by, now it's also self dot W. So this W is the dimension that these two are gonna do matrix multiplications on. Here comes our attention. In order to do the batch matrix multiplications, we can use the BMM, but we will need to do lots of transposings, which is kind of cumbersome. So I will be using the einsum function, which is much more convenient. It's torch.einsum. We are multiplying P and Q, and we're gonna specify the dimensions here. So our input has dimension batch size by 2 times the length of source by W. So I will say N by, let's call it M, and W. And for Q, it should be batch size. No, it starts with the 1, so let's call it O. O for 1, and batch size, and W, which will be casted to 1 by batch size by 2 times the length of source. So this einsum is actually a very smart function. It will automatically handle the transposes whenever necessary in the calculations, and this will be multiplying these two matrices across the W dimension, right? Because we don't have W here. So again, a little bit different from the introductions that was at the beginning of this video. In the introduction, there was only one direction for the encoder, but now we have bidirectional encoder. So there are two parts of the attention, and let's split them first. So let's say attention 1, attention 2 equals the, how about reducing the first dimension here. And at the last dimension, it will be 0 to length of source, which selects the first half, and the second half will be 0, O, and the length of source to the end. And now I want to introduce something called the mask, which is used to block the padded elements from the encode outputs. Since the paddings, they don't contain any useful information, and in order both to save some computational time and to maybe increasing some accuracy, we just block the paddings. So let's add an argument, mask, with default none. And let's say if mask is not none, then do this. Attention 1 will be this masked field that swaps any value in the attention1 tensor with a mask value of 0 with the negative infinity. The reason to use negative infinity is that our next step will be a softmax activation, which essentially puts the negative infinities into zeros. So in this way, it won't affect our later computations. Also, it will block the unhelpful gradients. So to be clear, this mask must have a same shape as the attention1. And so does attention2. Let's copy paste this. Attention2 equals attention2 mask fill, same thing. Then we want to concatenate them back. Oh yeah, we need to do the softmax in order to normalize the attentions into between 0 and 1. So we do f bracket f dot softmax attention1 at a dimension of actually the last dimension, and softmax of attention2 also at the last dimension, and the concatenation is also at the last dimension. And finally, we add back the redundant dimension at the zeros. And here comes our context. Again, we use the einsum function to do the Batch matrix multiplications. This time it's attention and encoder out reshaped. So now you see why I need to reshape the input output from this shape into, to take this 2 and put it into the dimension in the middle, because this enables us to compute the context vector. And our shapes will be, for attention, is 1 by batch size by, let's say, m. And for the encode output is batch size by m by hidden shape. And the result will have a dimension of batch by 1 by hidden dim. And this m again is actually 2 times the length of source. Now we build our input to the RNN layer. I call it let's call it a combo. Which will be the concatenation of our embedding the last hidden state at the last stack, let's do an unsqueeze to match the dimensions. And this context. And the concatenation will only be able to add the dimension of 2, right? So this I can clear it for you. So this context vector has a shape of batch by 1 by hidden dim. So this combo, finally it will have a shape of batch by 1 by embed dim plus hidden dim times 2, right? And now in order to match the input shape of our RNN layer, we need another fully connected layer for this combo. So let's add it here in our constructor. This one will have an input dimension of, we have just derived, and the output dimension will be the RNN input dim. So let's do combo equals f dot remove for self dot fc combo for combo. And our RNN, which will also be a GRU model. RNN layer. So input dim and hidden dim. This input dim is RNN input dim. And our stack drop out, and certainly batch first. So that we will do decoder output and our new hidden state is the RNN of this combo with a specified hidden state, which is taken from the last turn. Oh yeah, I did forget to mention that in the encoder, we did not specify the initial hidden state here, and it will automatically give zeros. But here we have to use the hidden states from our last turn every time. And just before we computing the output vector, which is again slightly different from the introduction, we are gonna do another linear layer here. So first we are gonna concat some tensors together. Let's do out combo, this decoder output. Let's squeeze the redundant dimension. This context again squeezing, and the embedding, squeezing the dimension of 1, and the concatenation is at dimension 1. So this just allows the network to work out some features that might help accuracy. And for this, the linear layer will be let's call it FC out. The input size is also hidden dim times 2 plus embed dim, right? Because here you have this decoder output, and there's only one RNN element going on. So this decoder output will have a size of, let's write it here. This decoder output will have a size of batch size by 1 by my hidden dim. This one is due to we are only feeding in one column at a time. And for the new hidden state, its shape will be the same as our previous hidden state, which is stack by batch size by hidden dim, right? So for this out combo, its shape will be, so we are squeezing this dimension, and this one has the last dimension of hidden dim, this context, also hidden dim, and this embedding is embed dim. So it's 2 times hidden dim plus embed dim, and at the 0th position is batch size. So this is our input dim of the FC out layer, and our output dim will be our target vocabulary size. Output dim. So decoder output. And because we are gonna use the NLL loss, which is negative log likelihood loss, we want to use log softmax activation here. At the last dimension. And we're gonna return this output, the new hidden. And yeah, we are gonna analyze our attention, so we're also returning the attention. Let's squeeze the redundant dimension and the empty self state, which is not used. Let's do none here.